So, we're talking in Chapter 8 about finding potential energy values. At least that's what we're going to start out talking about. Okay? So, we were talking about how our only equation for the change in potential energy is equal to what? Negative work. Okay? And then using that equation for work, we were able to figure out that we could use the integral, right, from x initial to x final of f of x dx, and that's how we could figure out what that change in potential energy was going to be. And we've talked about how when we're talking about potential energy values, we can really only take the change in potential energy between two positions, between two orientations. So I can have the remote here, and I can have the remote up here. I can't really talk about the potential energy value of the remote here, but I can talk about how the potential energy value of the remote changes from here to here. Okay? And last class, we did come up with a value for the potential energy of the gravitational force, which ended up being mg delta y. Yes. Now, sometimes, and we talked about this at the very end of the last class, I think, if we let some initial value of y be 0, and we let the potential energy, the gravitational potential energy, be equal to 0 at that point, then we can talk about the gravitational potential energy at any other point y, any other height y. Where? Here? That's a g. Yeah. Because it's the gravitate. No. I'll write it again. UG initial. Okay. Then we can calculate the gravitational potential energy at any height based on this kind of 0 line, this reference point. And that's actually what we're going to talk about in the problem that we're going to do. Yes. I know. But now Casey's like here for it, so she'll drive herself crazy trying to figure out what we were laughing about at that particular moment. Okay. Often we let this UGI that's going to be equal to 0 be the surface of the Earth. Sometimes we use another convenient reference point. So let's just do this, okay? So we're going to start with page 202, number 2. If someone would read a big chunk of that, and I'll tell you when to stop. All right, let's stop there for a minute. Okay. So, we've got a course, a roller coaster track that looks something like that. The first two hills here are at the same height h. And I honestly, In this version of your textbook, they insisted on putting numbers in, but I don't really want to do it with numbers. I want to do it with letters for a bunch of reasons. Probably the two most important ones are, I think there are going to be some comparisons that will be more easily seen if we use letters instead of numbers. And the second is that the AP exam does not always use numbers. Sometimes they use letters, and so you need to get used to the algebra and manipulating the algebra. Okay? So I'm going to call this point here 0 where it starts, and then we've got A, B, and C. And we've got our roller coaster cart of mass m that starts with a speed v0, or a velocity v0, I should say. Okay. And if we want to know the amount of work done by the gravitational force, what are we really finding? The negative change in the gravitational potential energy. So remember that I'm going to have to measure all of the UGs that are going to go into this formula from the same reference spot. So I should probably just set that reference spot from the beginning. And what do you think would be a good place to let yi be equal to 0 and ug be equal to 0? What do you mean by 0? We could, but I'm not sure that's going to give us negative potential energies, and there's nothing wrong with that, but I don't want anybody to freak out yet. I think C might be a better place for it right now. So we're going to let that. Well, you're getting a little head there if you're going to talk about kinetic energy. I want to make sure we get through the potential energy part, gravitational potential energy. And then when we do the lab on Wednesday, which is going to be the energy of a tossed ball, I'll start with a tiny little bit of lecture so that we can talk about the conservation of mechanical energy, because we're a little behind. It'll be okay. All right. Okay, so we're going to let UG and Y be equal to 0 down there on the ground. And then we can figure out the potential energy at every spot. Okay? So UG at 0, my initial spot is going to be what? My starting point. I only want to use the letters. No, this is 0.0 up here. So it's mgh. Okay, it's going to be the height, the y value above here where we let y be equal to 0. Okay. How about at point A? Yeah. So if we wanted to, we could call it mgya, but ya is going to be equal to h. How about ug at point B? Right, so it's going to be, we could say it was mgyb, but that's going to be mgh over 2, because yb is this h over 2. It's the height that point B is above where y is equal to 0. And how about at point C? Yep. Okay, it's going to be mgyc but yc is going to be 0 because it's not really any height above where we're starting. I'm sorry, it's not really any height above where we set y and u grav equal to 0. Okay. So now we can talk about the work. Okay. So part A asks us for the work done as the object goes from 0 to A. So that's negative delta UG. So that's negative UG of A minus UG of 0, because that's where we're starting, or O, or whatever you want to call it. So what's UG at A? Good. And what's UG at the initial point? We're MGH. So the work done as by the gravitational force as the object goes from its initial point 0 to A is equal to what? 0. So is there any work done? No, because that level above the Earth hasn't changed. So remember, when we're talking about potential energy, it doesn't really matter how I got there. It matters where I start and where I end, as long as my force is conservative. And the gravitational force is in fact conservative. Okay? So, let's try part B. What does part B want us to find? Right, the amount of work done by the gravitational force as it goes from the initial point, the original point, and point B. So again, that's going to give me negative delta U grav, or delta UG. So that's going to be negative UG of B minus the original value. So Gianni, what's the gravitational potential energy value at B? H. Good. And Sari, what's U grav UG at the original point? Good. So what are we going to get? What's my answer going to be? Maddie. Maddie, didn't you? MGH. Is that what you got, Sari? Over 2? No, it won't be negative, because this is the half minus the 1. So what's in the parentheses is going to be negative, a half. And then I've got the negative sign out front. Okay? All right, we got the feel for this? So part C is the change in potential energy, or well, is the work done by the gravitational force as we go from the original point to point C. So again, negative delta UG, again, negative UG of C minus UG at the original point. What did we say the gravitational potential energy was at point C? 0. And then the gravitational potential energy at point 0 was MGH. The negative signs cancel, and we get MGH. Okay. So somebody continue reading the problem for us. Okay, so have we already answered parts G and E? Because this was part of an omniscient narrator. I know that Zoe wanted to start with perhaps gravitational potential energy being 0 up here at 0.0, but I knew that later on we were going to have to set it here. Okay, so we figured out what those values are. So at A, we know that UG of A is what? MGH, and UG of B is MGH over 2. Good. Okay. And I believe there's even one more part to this problem. Okay. So, what do you think? Zoe. Zoe thinks it's, why do you think it's going to remain the same? Okay. So Zoe thinks that because the masses are the same, they're going to cancel out. Does anybody want to make another prediction for part F? Okay. So, of course, let's figure it out. So, if we look at our original conditions with the original mass, then I can say that I've got UGB minus UGA. Doesn't matter which order I take my difference in as long as I'm consistent between the original conditions and the new conditions. Okay. Well, let's see. So, UGB is equal to what? MGH over 2. And UGA is? Hang on. So what do we get here? Negative MGH over 2. I heard Sari say it, I think. Okay. And then we have our new conditions. And in our new conditions, we have twice the mass, right? So I'm going to take, again, UGB. I'm going to call it UG prime B minus UG prime A, because they're going to be different values if it's a different amount of mass. So if I'm doubling the mass, pretty much everywhere I see an M, I'm going to put in a 2M, right? So this is going to give me 2 MGH over 2 minus 2 MGH. Right? With me? I'm going to cancel those 2's. That's going to give me MGH minus 2 MGH, which is going to give me... So did the change stay the same? No. Okay. What happened is that, we increased the potential energy at both points, but we didn't increase them by the same amount. Okay, we didn't add the same amount to both of them. Oh, okay. Exactly. O and A would stay the same because they have the same amount of potential energy anyway. Okay. All right, we good? Okay. Now something else that Zoe was talking about at the beginning. was what would happen if we made UG be equal to 0 up here. I'm sorry, if we made U be equal to 0 up here, and then UG would be equal to 0 up there too. Okay, and we can do that. But then point B and point C would have a negative amount of gravitational potential energy. And that's okay too. So if we look at it real briefly here, right, here's my track. Okay, so if we let this point here be where U and UG is equal to 0, and we let up be positive, okay, so let's just real quick, we'll take point O and point B. Okay, so what's the gravitational potential energy at point O going to be? 0. Okay. What's the gravitational potential energy at point B going to be? Negative mgh over 2. Okay. But let's find again the work that's done as we go from 0 to B. Okay, so that's negative delta UG, negative UGB minus UG0. UGB is now negative mgh over 2. UG0 is 0. And what are we going to get? Is that what we got before? Yeah. Okay. So it really doesn't matter where you set y equals 0 and UG equal to 0, because everything that you're going to talk about in terms of potential energy is going to be the difference between two positions. So it doesn't matter where I put the 0 line, the difference is still going to be the same. Okay? Make sense? We good? Sorry. For part F, increases. Okay. I think we can do one more thing. In fact, I wish to do one more thing. Okay. So, there are other kinds of potential energy other than the gravitational potential energy. So, who's ever played pinball? What do you do when you play pinball? What do you do first? You pull the spring back. And what do you think you do when you pull the spring back? You're storing potential energy. And then when you let the handle go, I am. And what is that potential energy becoming? That's elastic potential. The elastic potential energy becomes kinetic potential energy. So of course, we want to talk about how we can calculate that elastic potential energy. And again, we're going to be talking about the difference in potential energy between two positions. Except that remember, when we're talking about a spring, we always let x equals 0 be at the natural length of the spring. So we don't have as much freedom here over where we let x be equal to 0 like we do with gravitational potential energy, where you can choose it to be anywhere that you want it to be. Okay, so let's just say we're going to start here at some position xi. And this is one of those respect the negative sign things because it doesn't really matter where XF is. As long as you are consistent with your pluses and minuses, everything will work out. Okay. Bless you. So remember that the only formula we have for the change in potential energy is that it's equal to negative work. And that's going to be the negative integral from x initial to x final of f of x dx. But if I'm talking about a spring, what's f of x equal to? Yeah, negative kx. So I've got my negative integral x initial to x final, negative kx dx. Delta u. I'm going to bring out this negative k, and it's just going to give me k integral from x initial to x final of x dx. Now remember, the integral symbol and the dx are like bookmarks, okay? Or bookends. And they tell you that the thing in the middle is what you're supposed to take the antiderivative of. So remember that this x is really x to the 1. So when we take the antiderivative of x to the 1, what do we get? 1/2 x squared. I take my x to the 1, I raise the power by 1, and I divide it by the new power. And remember that what I'm really doing is taking the antiderivative, so I'm undoing the derivative. So if I took the derivative of this, I'd bring the 2 down, my 2's would cancel, and I'd have x. Okay, but it's a definite integral. I'm evaluating it between two positions. And remember that we talked about this is also the area under the curve. So x initial and x final are my boundaries for taking that area under the curve. It's that line. It becomes that line. You'll see it as we go farther on in calc. Okay, so I'm going to bring out that 1/2 k. I substitute in my upper limit minus substituting in my lower limit. And I end up with delta U spring, or delta U elastic, got my little squiggly there, is going to be 1/2 k xf squared minus 1/2 k x initial squared. Please note that that is not the same formula as the work done by a spring. They are different. It is. It is, in fact, the negative of that because work is equal to negative delta U. Probably you need to use it in your Chapter 8 homework. Oh, well, you would use the work one in your Chapter 7 homework. Okay. Now, we do often say that will be equal to 0 when x is equal to 0, when that's going to be the natural length, or the relaxed length. And then we could say that there would be different potential energies at different points. Okay? So tomorrow is the quiz on Chapter 7. Wednesday we'll do lab. I'll talk for the first couple of minutes, and then we'll continue with the rest of this on Thursday. It's